optical fibers that common, and well, this is basically why these problems are so interesting, and there is a real physical motivation for them. Then there is the Horevo bound in 78, fiber amplifiers. Then in 93 there is a paper by Yuen where they consider something as, well, it will be similar to say that they solve the noiseless case, the noiseless channel, which is kind of the quantum equivalent of I mean, if solve this singularity thing I was mentioning before. So, I mean, they don't say it in the paper, but one can, in retrospective, say that. And in 98, there is all these joint, well, different publications where they have this coding theorem, which is the basic tool we need to address, start thinking about addressing the quantum, solving the classical capacity of any quantum channel. In 2001, this Gaussian conjecture was firstly mentioned somehow. So the idea is that for this bosonic channel that model fiber optics or amplifier, the optimal encoding will be using Gaussian states. And in 2004, Vittorio Giovannetti and collaborators solved the first case, the pure loss channel, which is a specific case, models as a very good approximation of an optical fiber. And okay, so but since then, most of the physical, well, all the physical interesting channels were not solved. Okay, so first, because this problem needs some kind of tools that maybe some of you are not very familiar with them. I prepare a bit of introduction. Okay, so to quantum optics, really just the very basic things I need to, that I will use later, so you understand what I'm writing. Okay, so here what we have is a Hilbert space that is discrete and infinite dimensional, and we call it the Fock basis, and where this n goes from 0 to infinity, and this n represents the number of photons of your quantum state. So a quantum density matrix will be written like this. Okay. Where I and G are a number of photons. As you may know, you have this annihilation and creation operators that are going down or up on the ladder of number of photons, and they have this satisfy this commutation relation. And you also have these position and momentum operators that also have a commutation relation, which with my notation will be 2i, so I take h bar equal to 2. You have different choices. The thing is, in this way I get the right, well, the shot noise in a nice way, the covariance matrix. Something important, so here is that we define what is called a phase space. So we have, which is kind of the same as in classical optics, where you have position and momentum. This is an oscillator. So, for example, in classical optics, or in classical mechanics, an oscillator will be a point that is just moving around a circle. Okay. But you could also see it in the framework, in the framework of the oscillator itself, and then you can just, in the reference frame of the oscillator itself, the state will be a point. Okay. And then if you could say, well, I could generalize to a probability distribution. So instead of having a point, I may have kind of a probability distribution on my phase space of my system. My system will be represented by some kind of probability distribution on this phase space. And when we move to quantum mechanics, what we get is a generalization of this, which is a Wigner function. And this function can be negative, which is different from a probability distribution. Okay. So something I need to define too is an operator, which is basically a displacement on this phase space. So it will take all your state and will shift it with some arrow all the plane. So this is a very important operator in all this theory. And why I need it mostly here is because to define this characteristic function that I'm going to use, which is basically the trace of rho times this displacement operator. So this is a quantum analog of this characteristic function you have in priority theory. Okay, and maybe a physical way of seeing it is through its Fourier transform. So the Fourier transform of this characteristic function gives you the Wigner function, which is the object I was mentioning before. That is kind of a quantum generalization of a priority distribution on the phase space.
So X is PQ. X is PQ, the vector PQ in this.
No, sorry, this is. Yeah, this is the. Well, this should be, yeah, this should be X and P. This should be a vector that is X and P. Something like that. So now I'm going to introduce the basic states you have in quantum optics. So the first one is a vacuum, okay, so 0 photons. And then you move to the next simplest one are the coherent states. And these coherent states are just applying this displacement operator to the vacuum. Okay? And we usually write them like this. So you apply some displacement to the vacuum. So, because we know in quantum mechanics you have this Heisenberg uncertainty relation. What this relation says is that the product of the uncertainty on X and P has to be larger or equal than 1, so some lower bound. So for the vacuum, what it means is somehow we have some uncertainty around this. So the mean of the vacuum will be 0, but there is some uncertainty on X and P around this center here for the state of the vacuum. For a coherent state, it will be this state displaced, is what I was explaining. So a coherent state is just something like that, again, where the mean of a coherent state behaves exactly as a classical harmonic oscillator. The thing is now we have some quantum noise around it. Okay. Then the next important states are the squeeze state, which is by the name means that you squeeze one quadrature. So the uncertainty on one quadrature is reduced from 1, okay? But the price you have to pay is that the uncertainty on the other quadrature is increased because you still have to satisfy this uncertainty relation. So somehow it will be something like that. Okay. And then another important pure state is what we call the two-mode squeeze vacuum state. Which is basically the equivalent of the Bell state, the one that we use as unit of measurement of entanglement in quantum information, and is written this way. So it's a superposition of n photons on one mode of light and n photons on the other mode of light in some amplitude that is a geometric series, okay? And then you normalize. And another analogy with the Bell state is if you take a Bell state and you trace one qubit, the other part is a completely mixed state. Here, what happens if you take this state, if you trace one part, what you get is a thermal state, which is for a fixed energy, is the state that maximizes the von Neumann entropy. So it's kind of the analogous situation as for the EBIT. So a thermal state will be something that is centered on 0 and then has a variance that is larger than 1 because it has much more noise than a coherent state or vacuum, something like that. Yeah, this is just for the introduction. So now I want to present what are the Gaussian channels. which is the things we want to study. Okay, so a Gaussian channel will act on the characteristic function of the input in this way. So what we get is something like this. So, so a nice way of understanding. So basically, you have to. It depends on two matrices: this K matrix and this Y matrix. And now I'm going to give you some kind of physical interpretation of this. So this K matrix, what happens is, if you take the vector of the mean of the state, what we'll do is you have to the output. Well, it transfers the mean of the state into this. So somehow it's some matrix that you multiply to the mean input and you get the mean of the output. So somehow it will be some rotation or some losses applied to your system. And then this and then how it affects the covariance matrix of the state in second order moment is this way. So basically, the Y matrix is some kind of added noise. In order to have your map to be positive, you will have some condition on this Y, some lower bound on this metric that will tell you what is the minimum amount of noise you need to add in order for your map to be physical. A way of seeing also why this Y is some noise is because, as I say, the Wigner function was the Fourier transform of the characteristic function. So if you do the Fourier transform of this, because this is a product, you get some kind of convolution. So this term here is just some noise you are adding to your system through this convolution. Okay. So this is the effect of this, some Gaussian noise. So the channels we are interested in well, for the ones we prove the result, are the what we call phase invariant. Which are the most physically relevant ones. Okay, and these ones have a very simple representation for this matrix. Basically, K becomes some constant times the identity, where this constant can be either, if it's smaller than 1, will be some losses, if it's larger than 1, will be some gain. And then Y is also some constant times the identity. So among these channels, you have the lossy channels, the losses channels, which are somehow you have your signal that enters the channel, and you can model the channel as if it was interacted with a thermal state. So you have some environment in a thermal state, and it interacts with your signal through a beam splitter. And then you get the output. Okay. So that's the lossy channel, and this is for this parameter tau smaller than 1, smaller or equal than 1, or larger or equal than 0. Then you have the amplifier, which are those who have a parameter tau larger than 1. And sting spin dilation of this channel will be, or well, this channel will be equivalent in this to an interaction also with a thermal state, but now not through a beam splitter, but through a unitary we call a two-mode squeezing operation, which is what you have in a parametric amplification process. So this is basically an amplifier. If you take in account the environment, will be this kind of unitary. Okay. So this is, for example, this unitary is what you get when you have a SPDC source, where you want to generate entangled photons. So you pump a crystal, and then you get pairs of entangled photons. So if you pump strongly, you not only get pairs, but you may have 2 and 2 or 3 and 3. So this is kind of the unitary corresponding to this process. And then you have the classical added noise channel, where tau is equal to 1 and y is larger than 0. So basically, what you are doing is you take your state and you are going to apply some random displacement to it, following some kind of Gaussian distribution, the displacements. And then, in addition to those, there is another class which is what we call the phase conjugation in a physical language. In the paper, they are called contravariant channels, gauge contravariant channels. And so these channels corresponds to this K matrix being again some constant, but now instead of being the identity as before, it will be 1 times minus a matrix that is diagonal and is 1 minus 1. Basically, what this does is this is the operation you do in a transposition. So, for example, when you want to do a partial transpose, this is what you do. You change the sign of the P quadrature on one of the two modes. So basically, what this operation will do is to take your, for example, a coherent state and move it to this other side. Okay, and so this operation is non-unitary. I mean, it's not physical. It's not anti-unitary, and then therefore you will need to add extra noise to simulate this transposition. And you need to add so much noise that the channel is entanglement breaking. So what I want you especially to remember is these channels are entanglement breaking. And something that is important and is used a lot in the proof is that, so all this family that I presented now can be decomposed. It can be represented in the following way. So instead of having your channel like this, and pick the one you want, you can find another way of, equivalent way of representing your channel through a beam splitter first. So you have your input that is now interacting with a vacuum environment, so it's different as before. It's just vacuum. You trace the environmental output. And then this goes through an amplifier that is again in a vacuum input, and then you trace this environment, and this will be the output of the channel. So by playing with the parameter, the transmittivity and the gain of this amplifier, you can reproduce all these three. Okay, you can go from a lossy to an amplifier or this classical added noise channel. And if you want to make this phase conjugation channels, what you need to do is to take the lower exit. So you trace out the upper exit and you keep the lower exit. And this is the way of getting this family. And this is something we are going to use later. Okay, this decomposition. So every channel of this family can be seen as this decomposition. So as I say, there was this parameter T, and I was not talking much about the noise these channels are adding. So here I want to represent, you can represent in a very compact way all this family, where you have here the noise on the y-axis, and here you have the determinant of the matrix X. Okay?
That'd be K.
Yeah, sorry. So you have, do you all see? So you have here 0, here 1. Okay, so between 0 and 1 you have all these losses channels that I was mentioning before. All the parameter tau between 0 and 1. Then between 1 and infinity you have the amplifier. Just exactly at 1, what you get is this added noise, and when the determinant is negative, it's just means that you have this other family of phase conjugation. Okay, and in order to have a map that is completely positive, what happens is the noise, okay, has to, you get a bound on the noise, okay? So basically y has to be larger than the determinant of k minus 1. Okay, so somehow you have a boundary here, and another one here, and here. So all the states that are in this region are non-physical. It means that there will be no physical map that exists in this lower part. Okay. And then we call quantum limited those who are just at the boundary. Okay. And those corresponds to the ones I was, for example, using in this decomposition where you have only vacuum as the input of the environment. Okay. So here this boundary corresponds to the pure loss channel. The one I was mentioning before, that is the case when you knew the solution. Okay. So this is this boundary here. This one corresponds to what will be a quantum limited amplifier. So it will be basically this scheme where you have vacuum here at the and you trace this output. So this will be the quantum limited amplifier. And this one here will be a quantum limited phase conjugation. And as I say, these channels are entanglement breaking. Okay. So one can also show, so this was to have complete positivity. Then you have a condition for being an entanglement breaking, a channel that destroys, so you have a bipartite state and assign half of it to this channel, the output will be separable. So that's the definition of entanglement breaking. And you have these conditions. Okay. So the absolute value of the determinant of k plus 1, so y has to satisfy this condition. And you can see that basically, as I say, these channels are entanglement breaking, and then there is always a mirror channel on the other side that is also entanglement breaking. So this condition here gives me this boundary. So all the channels here will be entanglement breaking. And it's somehow, if you know that these are entanglement breaking, it's easy to see that this boundary is also entanglement breaking, because basically what I'm doing, if I do a transposition after my channel, what I'm doing is moving from here to there. And of course, if my channel is entanglement breaking, the composition of the two will be a physical channel and also entanglement breaking. So somehow this is explains why you have this other boundary here. Okay. So basically, what we knew before we started this workshop is that if we were able to solve for these quantum limited amplifiers as we had solved for these ones, we get everything somehow. That was what we knew, and this is what I'm going to explain a bit now, and then I will come up to the final part of the proof. So does anyone has a question about the channels, or something was not clear? No? Okay. Somehow I'm going to explain it in 3 steps. The first step is kind of was common knowledge for many years, but I think it's maybe important to stress that what we really want to do is to calculate the capacity, and everyone was talking about this minimal output entropy conjecture of that vacuum was minimizing, but why? I mean, so maybe I explain this first. So first there is a reduction to the this minimal output entropy conjecture. Okay. To do that, so first I need to define the Holevo capacity of these channels. So it will be, so for my channel n, I need to add some energy constraint, which is something that we don't usually have in qubit capacities. But in this case, you will have to consider that you have a finite amount of energy for your encoding. Okay, so it's a reasonable assumption. And then what you have is, this is you maximize over the average input to the channel the following quantity, the von Neumann entropy of the output, the average output, minus some minimization of the average output entropies, okay? Where basically there is an ensemble of pure state inputs, okay? So these pure state inputs and these probabilities give me some ensemble, so are some ensemble that on average give me my rho, the same rho I mean the average input. That's the condition. And we know that in quantum Shannon theory we are not as lucky as in the classical one, so this doesn't give you the ultimate capacity, but we need to regularize for some channels. So in general, to define the capacity of the channel, we need to take some limit of n infinite uses of the channel of this Holevo capacity, where now you take n uses of the same channel and n times the energy you had. So I mentioned that before that the pure loss channel was known, the solution, and indeed one can see it very easily from already from here is basically because the dilation of this channel is a beam splitter, because I have my input, I have vacuum here because it's a pure loss, I say it's a quantum limited, so my environment will be vacuum. And we know from quantum optics that if I send a coherent state through a beam splitter, I get at the output a coherent state, which is also a pure state, which means that a trivial lower bound to an output entropy of a channel is 0. And it happens that in this case we are lucky and we have it. So somehow you make this 0 by just using coherent states, and then this you maximize it because for a given energy, the von Neumann entropy is maximized by a thermal state. Okay, so the average output state will be a thermal state, which means that because the channel is Gaussian and is of this form, the input state also will be a thermal state. Okay, and we know that we can obtain a thermal state out of coherent state, basically because we start from small circles like this, and from the vacuum. And we just do random displacement following a Gaussian distribution. So this is a way of obtaining a thermal state out of coherent states. So basically we are done. We have an encoding that is based on coherent states, where the average input state is a thermal state, and that achieves the capacity for this pure loss channel. So for the pure loss channel, somehow the capacity is given by this function that I'm going to define now. So tau will be the losses parameter of my channel. E is the number of photons I have per use of the channel. Yeah. So that, and where this function g is just the von Neumann entropy of a thermal state. So you can calculate it and it gives this. So somehow, for the rest of the channels, what we wanted to prove is that indeed the same encoding is still optimal. So still using coherent states modulated with this Gaussian distribution, we were expecting this to be the optimal. I mean, we had strong evidence that that was the case. So somehow. So that's optima, and this is kind of the conjecture. So put a.
Isn't the formula just g of tau times e?
Depends, because here yeah, you are right. So the thing is, yeah. So here I'm writing it as a function of the variance. So this will be the variance of the input thermal state times the transmittivity plus the added noise from the y. But it's true, then I have to define g in a different way. So instead of x, so yeah, I was so instead of the x here, I guess. So this is okay, but this is the von Neumann entropy where x is the number of photons. So what I need to do is something like that. So x will be equal to the variance minus 1 divided by 2. Okay, so there's a connection between the two. So let's put to say that is different. Okay. So now what we do is we try to find an upper bound of this quantity. A way of finding an upper bound is to say, okay, I maximize the plus part and I minimize the lower part. Okay, for a general channel. So of course the maximization we know is the same trick as before. For a given energy, the maximization of this thing will be still a thermal state. Okay. Where now I may have a different noise added because the channel is different from this pure loss. And this tau could be some gain, for example. And then somehow I lower bound this part. I lower bound this part with the minimization over all pure states of the output entropy of my channel. So at this point I just have an upper bound. Okay. The thing is that so what the conjecture says. So if you were able to prove the following, if you were able to prove that this quantity is minimized when you input vacuum. Okay. So So if this is true, which is what we were looking for, then you can see that this upper bound is indeed tight, and then is given, I mean, this will be given by this. Okay. Which in the case of the pure loss, it happens that it's because it's a pure state. This is 0. The minus part is 0. So somehow the approach is, as I say, is the following. You find an upper bound, and then you conjecture that vacuum is the one who minimizes this output entropy. And then what was before a lower bound, because the coherent state encoding is always a lower bound, the rate of this lower bound corresponding to coherent state encoding will be equal to the upper bound you just get if this conjecture is true. So if you prove this, what you get is an equality. Okay.
There's also the additivity question, right? There's a minimum output entropy. You're assuming there's an additivity.
Yes, yes. So what I should have written is that this is n. I mean, that was a typo. So I put the n here. So it's the question really we need is the minimal output entropy of n uses of the channel, and the conjecture will say that vacuum a vacuum on everyone will minimize the output entropy of those, because then we get this, and I mean, and so I'm talking about the ultimate capacity. Okay. Of course, if you prove that it's additive, then you can reduce to the whole level. So what I'm going to present now is somehow a second reduction that reduce the complexity of the problem from n uses of an arbitrary channel to a single use of a very specific one, which is I think an important step, and the channel that we are reducing to will be this quantum limited amplifier that I was mentioning before. So this was some work I did in the last years in collaboration with Nicolas Serre. So I'm going to so the key idea is this decomposition I presented before, that any channel can be decomposed into a pure loss channel and a quantum limited amplifier, and using also the property that the pure loss, that vacuum is a fixed point of a pure loss channel. Okay, so the intuition is that if you have a beam and you start removing photons, at some point you get nothing on the vacuum. So that's so I want to lower bound this, okay? And as I say this, so can be decomposed every channel into an amplifier and a lossy channel. So I will have n copies of amplifier preceded by some n copies of some lossy pure loss channel. Okay. But I can write this. I mean, this is a pure state, and I'm applying some CP map into it. I get at the output some mixed state. It's a mixed state that I can write in a given decomposition. I may not know it, but I have the right to write this. Okay. The output state of at the middle. Here, the state will be mixed. Okay, here. Okay, so now I take the sum out because because of linearity of the maps. Okay. So basically, what I'm left with is this. Okay. I mean, I'm just taking the sum of this outside after the map, and then I use the concavity of the von Neumann entropy, and then I can take the sum outside the von Neumann from inside to outside. So I can write this. Okay. So now the next step is to realize the following fact, which was known, it was published, well known. So now we are at this step where we have this is our input, and we are applying this unitary. And I told you that this exit, if you see this as a channel, you trace this part, this exit is entanglement breaking. So the other is a complementary channel, a channel that is complementary to an entanglement breaking channel. So basically, for a given pure state, the spectra of the two outputs is the same, or the von Neumann entropy is also the same. So the state that minimizes one minimizes the other. And we know that that the minimal output entropy is additive for these entanglement breaking channels, or the complementary ones. So basically, what I can do now is do the following. I can lower bound this by n times the state that minimizes the output entropy of a given amplifier. So I can write this n times the minimum over pure states. Okay. This was using the fact that that the amplifier is complementary to entanglement breaking, and therefore is the mean output entropy is additive. And then the thing I do is call my weaker conjecture, is to say, well, I hope that vacuum will be the one who minimizes the output entropy of this channel. Of course, this was not known at that time, and this is what has been proven now. I mean, what we have done in the last weeks. So somehow we conjecture this. Okay. So n times this, and this is, for this we need the conjecture of the amplifier. Okay, so it's still something, it's just still a reduction to another problem. The thing is, this is a lower bound, so it could be that it's not tight. Okay, so you still need to do a further step, is to prove that this lower bound is indeed tight if this conjecture is true. So basically, what you have to realize is what I said before. Vacuum is a fixed point of the beam splitter, of this pure loss channel. So if I inject vacuum here, I get vacuum, which is the state that gives me exactly the lower bound. So if this conjecture is true, not only vacuum minimizes the output entropy of this, but it minimizes the output entropy of this thing. Basically, it means that the two output entropies for the vacuum is the same for the amplifier, or the concatenation of lossy channel and amplifier. So what I'm saying is the following. Well, maybe it's so just by realizing that when you input vacuum into this concatenation, which is equivalent to your channel, you get what I was writing before. So this is an equality indeed. So the output entropy of the amplifier when you input vacuum is the same as the channel N, which is the combination of the two. And now this gives what I was showing before. So I want this okay, with an n, and you get it, but for that you need to prove the conjecture for a single use of the amplifier. So we gain in two ways. We gain in the fact that now it's only one use, not n, and it's a very specific channel, not any arbitrary n. Okay. So now I'm going to explain the last part, which is a very beautiful idea by Vittorio Giovannetti, and it is based in a crucial observation that is easy to maybe easier to explain here. So as I say, so we have an amplifier. We want to solve an amplifier to prove that the minimal output entropy of an amplifier is minimized by vacuum. Let's take this amplifier of gain 2, okay, which is quantum limited and is here. This one, instead of solving for that one, I can solve for the complementary one, for the phase conjugating one, which this you have to trust me, but is the one who corresponds to -1 here. The determinant of k will be -1. So if the gain is g here the parameter tau will be g -1. Okay. So it corresponds, for the specific case of gain equal to 2, corresponds to the determinant of k -1. So, and it's quantum limited, so it's here. Okay. So I have the complementary of this one is this channel here, and both have the same output entropy. And now what you do is to say, well, I apply it's an entanglement breaking. I apply a transposition to this channel after the phase conjugation. This operation is not going to change the eigenvalues of the output of the and it preserves the von Neumann entropy. So basically, what happened is you can build a new channel that has the same output entropy, but now is here because it's concatenating my phase conjugation with a transposition that is moving it here. Okay. There is maybe a way of seeing this is one way of building this channel that are phase conjugation. They are equivalent to the following scheme. You have your input, you do some measurement on the coherent state basis, because it's a prepare and measure scheme, because it's an entanglement breaking channel. So you measure on the coherent state basis, and then you modulate vacuum with some x and p values, depending on the outcome of your measurement, and then you send this state. But when you want to do a phase conjugation, what you do is, depending if you get some, when you measure p, what you modulate, what you send out is you have to change a sign of -p. Okay. So because this is similar to, this is in order to simulate this minus sign here. This minus sign, what does is to flip the sign of the p quadrature. So somehow I measure, I get some data for x and p, as I change the sign of p, and then I modulate a coherent state with these values and I send it. But, so this is this channel. This other one is the one where you just don't change the sign of p. So they are very, very intimately related somehow, if you see it in a prepare and measure scheme. The thing is, this channel is no longer quantum limited, and because it's non-quantum limited, I can decompose it again. So I can decompose it into a pure loss channel and another amplifier. Okay. And the thing is, you get some magic happening, and the decomposition gives you the same amplifier you were starting at the beginning. So basically, it goes to the previous amplifier, and then gives you, in this case, so it's a decomposition where you got a pure loss channel, So you get a pure loss channel followed by an amplifier which has the same gain as the amplifier you were starting with. So you have done a cycle from your amplifier to the complementary transposition, decomposition, and you return to your amplifier. Okay, and this is the key idea that I'm going to use. So I give you the intuition. Okay, so I'm going to rewrite what I was just saying with words. Okay, we have an amplifier gain G, and now because it has a complementary that is a phase conjugation of parameter tau G minus 1. But the von Neumann entropies are the same because they are complementary. And now I do the transposition, and then I have this new channel. Again, is equal because and now this one, as I say, is just the channel here that I can decompose. Okay, so now you decompose it into an amplifier of gain G preceded by a lossy channel of transmittivity G minus 1 divided by G. And I stress again that this works because...
Should it be a piece of G minus 1? Sorry, for the third step.
Sorry?
It's a G.
Yeah.
It's the same thing.
Yeah. So I stress again because it's very important. This gain is the same as the one we were starting with. Otherwise, it doesn't work. And so it's okay. I'm just rewriting again the same, but to make it more compact. So now one can play the same trick as I was doing here, of taking the exit of the lossy channel as a mixed state, decomposing into pure state, and just play the same trick. So one can then get a lower bound that is like this. Okay. And now if you look at this, you may think, well, we haven't got anywhere because we have still the same problem as before. I want to minimize the output entropy of my amplifier. Looks like we are not progressing much. But the trick is the following observation. Okay, that is this pure state here. Okay, is such that the average of this pure state is the exit of applying a lossy channel to your pure input state. Okay. So this is a set of state that is not the whole ensemble of pure state, but a sub-ensemble of them. And the thing is, we are again with the same amplifier, so we can iterate. So, and that was again a very good idea of Vittoria. So you can return here and play the same trick again, but now you get not one lossy channel, but applying two of them in a concatenation, and you can continue forever. Somehow the intuition is that at the end, this vacuum is a fixed point of this channel. So basically, this converges to vacuum. So basically, this has to. So this is will be lower bounded by the, well, not much space. So at the end, somehow you get this. You get what we wanted. Okay. This can be made more rigorous using an argument that is on page 18 of the paper, if I remember correctly. So you need to argue that we are considering a finite amount of energy, so there are states with finite energy, and in order to find this lower bound, I mean, this is a bit of technicality, but it's very simple. But somehow the key idea is what I explained now, is this decomposition that happens, as I explained before. You get the same amplifier after the decomposition, after doing all this trip through the channels. And then you can iterate, and then you have a restriction on the states where you are minimizing that goes to the vacuum at some point. And it has to be satisfied for any n, because we can iterate the process as many times as we want. So of course, vacuum has to be the state that minimizes the output entropy of this amplifier. Okay. So that's what finished the proof. I want just to make 4 more remarks, and we are done. So in addition to this, we get some corollaries. Okay. So one is about entanglement formation of Gaussian state, because well, maybe some of you know there is some connection between somehow the thing I was writing here can be seen as an entanglement formation of a given state, and therefore we can build some. We can by getting this result, you can also give the entanglement formation of some Gaussian states that are those who are a thermal state, vacuum, that you send through an amplifier. So this Gaussian state here at the output, by this result you can give the entanglement formation, which was not known, because the only Gaussian state we knew the entanglement formation were those who have that are symmetric under exchange of the 2 modes. Okay, so these are non-symmetric, and as the first cases we can give the entanglement formation.
So the Gaussian states have a decomposition like channels as well? If you have this, for phase insensitive channels, you have this decomposition. So for Gaussian states that are like phase insensitive, maybe it's a naive question.
I don't know if you can do something like that. What I can know, I can tell you, sorry, is that all the states that will have similar maybe properties as that are maybe invariant on their some rotation on Alice and the conjugate on the other one, you can build them always out of thermal state that you send through this amplifier, and this is a particular case of those, but I don't know.
I don't think you need the loss part. It's just another thermal state. Okay.
So there is apparently some corollaries also concerning Discord that I haven't taken time to check. Then, as you know, last Friday there was another paper by Andreas, a postdoc of Vittorio and Olevo, that generalized this this proof, and they in addition get some majorization results. So basically, that the state you get at the output when you input vacuum to this amplifier will majorize the others. Okay, so it's a stronger proof, and you don't need this energy restriction that I was mentioning. But for the capacity, the energy restriction is fine. You don't need more. And then the last thing I want to mention is that there is a PhD student in Brussels that has been also working on trying to solve this conjecture in a very different way, of course, much more technical. and there seems to be pretty close to habit or even habit. So this is the last comment I have. So thank you.
Well, thanks for this nice exposition and the insight in the proof. If there are questions, comments.
You mentioned before the entanglement of formation of a state. Do you mean entanglement cost, or is it additive in this case, or?
Maybe for this case we can even claim entanglement cost, maybe because of the additivity I was mentioning. Yeah, that's the thing is. So the approach I wanted to use to prove this was solving some entanglement formation problem, and I was focusing on two modes. But it's true that if you get this additivity, well, probably for those states you can probably claim that the information is equal to the entanglement cost.
So additivity here kind of follows from sub-additivity of the first part and the kind of like additivity of the second expression.
It follows from the.
In specialized literature, this is called the MSW trick.
It follows from the additivity of the.
I think
Yes, it was this MSW trick was popular.
So it's
some time
kind of
ago.
it shows that you can write it as an entropy minus an entanglement formation. And Gaussian states are pretty special because all you need is somehow a minimum element, and then if that is Gaussian itself, then you can just use this place to make the ensemble decomposition.
If you restrict to starting from Gaussian states, this Gaussian entangled formation. Yeah, this is not difficult to calculate, but it's of course an upper bound.
So what's the next
conjecture.
difficult case that is not covered by this? I mean, like
The following, I think the simplest, and I believe it should be. You will need new techniques because it's very simple. You have a beam splitter, you input vacuum, and you have some rho that you fix the entropy, not necessarily zero. So it could be a mixed state. And you say the von Neumann entropy of my input is whatever value. Then you want to prove that the output state, the von Neumann entropy of this, will be minimized when you input a thermal state of same entropy somehow. So you get something like that. Yeah. Okay. And well, this channel you cannot decompose it because it's already quantum limited. And so I believe to prove this you need something different. And then there is other conjecture that kind of combines both. So then you put a thermal state here and you can ask the same question, which is a bit more complicated. These are on the PhD thesis of Saikat Guha, chapter 4.
And in terms of channel capacities, I mean, what's the simplest channels for which we do not?
So these cases I mentioned this phase invariant, and you can get a bit more. You can consider all one mode Gaussian channels, but the price you have to pay is that you have some kind of energy threshold. So if you have more energy for modulation that above this threshold, this proof will imply also the capacity of those channels. But if you are below the threshold, we don't know. So there are still one mode cases where, I mean, the thing is why we don't know is because this trick of upper bounding doesn't work anymore, because the state that minimizes the output entropy will need more energy than the one you are allowed to use. Will be a squeeze state, for example, that needs so much energy that you are not allowed to generate it. So in that case, we don't know how to solve it.
So can I understand this as actually using your channels there, but with a different cost, energy cost?
So these other channels, more general, are again the same, but this is still at the middle somehow, but they are preceded by some Gaussian unitary,
Yeah.
and followed by a second Gaussian unitary. This unitary you don't really care much because it's on the measurement. This one you care because if there is some squeezing, it means that your encoding will need squeeze states. So the ugly part is this one. So we have a paper
It's true
on
that
that.
you can think of this U1 affecting the energy function and not the channel.
Yeah. Yeah, that's the thing, that the state that minimized here is vacuum, but if this is a squeezing operation, the state that will be optimal here through the whole process will be a squeeze state. I mean, of the squeezing opposite to the one of the unitary. So you get vacuum here. And then a squeeze state needs energy. And if you are allowed less energy than the squeeze state itself, then you cannot achieve this lower bound that was. So this trick of finding an upper bound that then matches the lower bound in the Gaussian case doesn't work for this specific channel. So you have to do something different.
Okay. Okay, let's thank Raoul again.
Thank you.